But I want to say a few things. One is that, you know, in research we have these ideas and we publish maybe a paper and we say, oh, job well done, and then we go on to the next paper. But often in industrial research we get to take that next step, which is to really drive the idea and really make it work in practice. And I really appreciate having people like Don who take an idea all the way through and are committed to seeing it to go into production. Now that the C# generics are well on their way, he's turning his attention back to F#, which is this functional programming language. And in fact, we have this tool that we built based on a camel that he's now helping us to port on top of F#. And I really look forward to hearing more about it, as we're quite a big fan of the approach.
Okay, great. Thank you very much, Tom. That's lovely. Thank you. So I'm going to keep things fairly simple today, which is just to introduce sort of what F# is as a language, give you a taste for why I am a big fan of ML-style programming, and why I've gone to the effort of doing a language implementation on the .NET platform. So it's not really sort of a research talk, right? It's really, F# is a site in which to do future research. I've written a paper recently about, say, the problem of mutually recursive initialization in safe programming languages, and which is related to, directly comes out of actually trying to program sophisticated GUI applications in a language like F#. And so research comes out of this kind of work, but I'm also very keen to have a practical programming tool for people who need to do symbolic processing in an ML-style language in the context of .NET, exactly the kind of application that Tom was talking about that they've written, the SDV, Static Driver Verifier application. So let's just really go through sort of what is F#. I'll give a demonstration of what is ML programming. I'll talk about how the ML approach to language design of sort of a simple set of features, making sure they're orthogonal, is basically the approach I've taken to F#. And then my philosophy of languages in the context of .NET, and in particular this notion that we don't have to think of languages as being in competition with each other anymore, but we can think of them as much more being sort of symbiotic. They work together in a lovely synthesis of different programming, different aspects, tackling different aspects of the programming problem. And I hope you can see how that works in the context of F#. So let's just do a fairly straightforward functional programming example in F#. First I'll say there's a competition for the design of the F# logo, which you will see flashing up there. I don't know if you saw F# for Visual Studio. We'll just watch quickly in the bottom right-hand corner. So this is spectacular. one more time. Here we go.
Where are we supposed to watch again?
You watch about right here.
Okay.
Right. It's a very, very bad logo. So let's create a new project. So the job is to create to do symbolic differentiation in of simple expressions. So we've created an F# project. We'll add a new item. So we'll create an F# source file. Gives you some very unhelpful hints about how to write F#. That's not a particularly good starting point. Right, so delete all of that. So type, let's define a type of expressions. The first one will be, say, the sum of two expressions. Expressions are expression, or the product of two expressions, or a constant of, we'll make it a double, so that's the same as system.double, or a variable. So we'll make these multivariable expressions, so the variables will carry the name, which for instance will be a string such as variable x. We'll just do, in all the examples, the variables will always be x. So there's a simple type, a simple language of expressions, and let's define the most obvious first thing to evaluate one of these expressions in an environment as an expression. The environment will give us bindings for the variables, so we better decompose what the expression is. Match expression with, well, if it's a sum of we'll do the constant node first, constant C goes to C. Okay, so it's told us there, the red squiggly here just tells us that this is an incomplete pattern match, that we've got extra cases we haven't considered yet in this bit of a program. So let's do the sum E1. What do we do? Yeah. Thanks, Eric. Was that where there's a nice to-do there, which the S source depot is available. Yep, you've got write access. I can give you write access in half an hour. There we go. So let's do E1 plus eval and E2. That is the one. Yep. Let's do products. E1, E2 goes to eval E1 plus times E2. Yeah, that's right. Variable V goes to, well, what are our environments going to be? The environment had better be, we'll use a type of maps implemented as binary trees, so maps from strings to floating point numbers will do. I'm giving you the type just to explain what the type actually is. So the type, this is a functional programming view of dictionaries, so immutable dictionaries based on binary trees, which comes out of the box in the functional programming library that comes with F#. And then we'll go map.find the variable in the environment. Now there is actually a type error here. So ML-style languages, for better or worse, don't support ad hoc operator overloading. And so plus is plus over integers, and they use a different operator for addition over floating point numbers. That's just part of the ML language design, at least as I've taken it. We also, this is a recursive function, so we better put letrec in here. So ML languages always have restricted, so they want you to be explicit about the scopes of recursion, although it is feasible to implement mutual recursion across all the modules, the top-level modules in your program, but when you have inner scopes, bindings within inner scopes, they want you to be explicit about the scope of the recursion. So well, that's just, you have to be explicit about how far the recursion extends. So the recursion extends across this binding, the binding for eval. Okay, so then we can define some expressions. Let x equal the variable node x. Oops, what's that? Let the square of an expression equal the product of an expression. And then we can do something like console dot write line the res equals not comma eval. We need an environment. Let's just build up an environment that map.add the binding x to, we'll map it to 31415. And we're adding it to an existing map, so we use map.empty. Now let's evaluate the square of x in that environment. So it's going to complain unmatched. There we go. It's going to... No, x is the variable here. So it's actually an expression here. Is that... Yes, that's right. So it's complaining there's a type mismatch here. You do have to be explicit about boxing in this language, so there's no auto boxing. And that there's no overload that takes a double in this position, so it's asking you to be explicit about the overloading. And we should be able to build that. And start it. And the console window flashes up with our result, which is good. Okay, so let's write symbolic differentiation now. The derivative of an expression. Let's match the expression with the sum of E1 and E2. Well, we better differentiate. So we're going to get the sum, the symbolic expression containing the derivative of E1 and the derivative of E2. The product of E1 and E2 is going to be the sum of the product of E1 and the derivative E2 and the product of E2, the derivative E1 and E2. We better derive that. That one, fix that one there. Okay, that's good. So we've still got an incomplete match. Fill in the remaining cases. Const of C goes to const of 0.0. And the variable v, well, we better actually take a derivative, a partial derivative, with respect to a particular variable, such as there. So we better fill, I'll fill those cases in. So if v equals var, then, oops, v equals var, then const of 1.0, else const of 0.0. Okay, we've left off some arguments here on the recursive calls, so we'll go fill those in. Oops, we've also got, yes, I could have done a nested function at that point. So we also got the definition wrong. We've got the E1 on this side, so we better not take the differential of E2 on that side.
Another thing, you want refactoring in your...
Yeah. Thanks, Eric. Yeah. Good. So I'll assign that bug to you, Eric. Yeah. So let's evaluate the derivative with respect to x of the square function there. We'll just make sure we've unmatched. Aha, thank you. Unfinished, yes. Debug, start. And you saw if we didn't lose the console window, debug, where is it? Debug Windows, console, there's 2π as a result, as you expect. Okay, so that gives you a taste for symbolic programming. I mean, this is only using algebraic data types and recursive functions and the pattern matching and so on. But you get a sense for why symbolic processing is actually, programming is extremely easy in this context, and why you can write sophisticated algorithms over the particular languages that you're dealing with and sort of control the complexity of the algorithm. It's easy to scale this up with a larger language. So I'll switch over to an example, a more fleshed out, pre-baked example of the same sort of thing, where the aim is, first of all, to define, we'll actually define an extensible language at this point. So sometimes in ML you deal with closed languages where you can write more and more sophisticated algorithms over that closed language. Sometimes you go for the other direction of extension where you can extend with arbitrary operators where you give the particular semantics that you want for those operators as part of the specification of the operators. And these are two different notions of extension. And of course it's well known that it's quite hard to do both sort of extensions in a programming language, and they correspond exactly to inheritance or to discrimination. And this is just showing how you can extend this example where we bake in the semantics that we want of each kind of operator. We want evaluation, we want differentiation, we want printing, and a name, which is effectively defining what you'd think of as an abstract base class in an object-oriented language. So evaluation over that language is fairly straightforward. At the most interesting node, such as unary operators, we just call the evaluate sort of method of the function value for the operator. And differentiation of the unary operators just follows the chain rule, of course. That's nice and compositional, which is why this example works well with this mode of extension. So you just take the product of the derivative of the derivative of the expression, the derivative, and the differential of the expression. So then we can define some particular operators, such as the negation operator, which has a derivative which is constantly -1. Sine and cos are mutually recursive. So sine, the derivative of sine generates cos, and the derivative of cos generates the negative negation of sine. And the evaluation functions, of course, are just the out-of-the-box functions that evaluate over IEEE numbers. And you can define powers of n, and you can define polynomials where the list gives the coefficients of the polynomial and square and cube and so on. And the derivative of e to the x is just a recursive function, that is e to the x. So a very common sort of thing that people want to do is to optimize and transform expressions. And this is showing just a prototypical example of how this sort of thing is done. We're going to compute whether we can, whether an expression is a known value or not. And you just have these recursive calls to the optimizer, which are simply collecting these, a pair, the optimized expression and a summary of information that we've learned about the expression. Then we just find out whether if both of them are known values, then we can return a known value of the sum of those two, and then eliminate nodes involving addition of 0. And so on for products. And in this case, optimization works well with our notion of a unary operator, because if we can optimize it to a constant, then we can just call the evaluate function on the constant in order to generate the result. So we can, of course, have a function to print expressions to buffers. And then we have expressions to strings. And then we have derivatives with respect to x. So then we'll switch over to a small example, again written in F#. This program could be just as well written in C#, but I chose to do it in F# just to push it a bit. So we want to define a GUI just to do some simple plotting. I didn't quite have time to do the DirectX example for multivariate kind of displays, but so I just did the two-dimensional case. So you can see a lot of the idioms that you'll be used to from C# programming. Here we have the notion of using. I mean, these sort of idioms you don't put them directly into the language, but you do code them in a way. First of all, you have to tell it that the pen is an idisposable object, and then you kind of give the continuation that gets called when in the scope of the using operation. So that will cause idisposable as this action completes, or if an exception is thrown. So this also is here how we create our new form, and we set properties on the form, and we add some event logic to a window, to our form. We add some menu items, one menu item for each expression, and then we draw on the refresh operation here. We draw the expressions just projecting in and out from the floating point numbers onto the grid. And then the key function here is this is actually calling our differentiate evaluator. No, not the differentiator, the evaluator for the expressions. And we draw lots of points.
Yeah, and
yeah.
Eric has an S, so I'll ask, do you support, editing of the graphical, the back and forth?
No. So the GUI, plugging it into the Visual Studio GUI designer is
Eric's going to do that.
Eric's going to do that. Then we have some test expressions down here, and we'll have a function that augments each of these test expressions with its derivative and its second derivative, changes the color to be, and the first derivative gets a dash, and the second derivative gets dash dot, and then creates a form for those expressions, and off we go. So let's start that. So we now have menu. So for instance, we have x cubed here, and the derivative of x cubed is 3x squared, and the second derivative is 6x. These are, on the right, we see the optimized expressions and the printout of the optimized symbolic expressions that have been computed by F#. And the optimizer in this case doesn't deal with associativity of the times operator, so which is why it hasn't done 6 times x. So the bracketing is not shown by the printer, but the bracketing is to the right in this case. So let's plot a few of these. So e to the x is there, the derivative is there, and the second derivative is there, as you expect. The x cubed is there, squared. And so there's the second derivative, and so on. Let's do one more. That's a nice one. X times sine x squared, and then the derivatives get more and more wild as time goes on. Okay. So that the last thing we'll look at here is accessing this stuff from C#. I haven't gone through and written the whole GUI, rewritten the whole GUI in C#. So instead what I'll do is, first of all, we want to compile the ML code as a DLL. Okay, so we better change that over and build that. So we'll be able to access it from C#. And then, so you can see here how we can use the functionality. In fact, if we look in the object browser, it should also be here. So my library, and this is the functionality defined in the ML code. So we have our cos operator and all the rest of the stuff that's available in the ML library, and you can access that directly from C#. So we should be able to go diff dot, and we can see what's available in the ML code. And in this case, we're just printing out, just doing a simple evaluation of a derivative, so we'll build that one, much like we did before. And do we set this as our startup project? We start that. Okay, and that's just a typical .NET multi-language sort of example, except in the context of C#. Let's have a look at our.
Can you cross-debug this way instead?
What's that?
C# to
yes, you should be able to. Though we did have bugs with stepping into F# code, so just yesterday. So what I'll do is actually I'll do something that I know works, and set a breakpoint on the computation of the derivative. And so there we go. We've hit the breakpoint we started in C# and we've hit the breakpoint in the ML code. And we'll try doing some stepping. So the first one was a unary operator. We called into the derivative. Okay, the first one was actually cos, and we're stepping in and we're differentiating cos, and so on. The second one is a Syme. Okay, however it works. Okay. So that I hope has given you a flavour for ML programming and F# in the context of .NET. So I'm going to talk a bit about where the sweet spot is, and then about the ML approach to language design. So obviously it's in symbolic processing is where ML is very, very nice. So these sort of applications, writing compilers, writing transformations, complex transformations over programs, optimizers, doing static analysis of programs. And it's often used by people in the sort of developing theory-based tools such as verification, model checking, and theorem proving. So ML, let me actually go here. ML is used inside Microsoft. It's used for the Static Driver Verify project, and I think that the success of that project is related to the use of ML, and not totally dependent on it, but it is related. Is used. People sometimes write descriptions of systems in order to help them clarify their understanding of the system. So high-level models, high-level implementations of prototypes of a system. So someone did that for the file replication service. Nikolai Bjorner did this. We have the Zap Theorem Prover at MSR and other tools that are coming out of MSR, and I've used it for a lot of my work. So the aim of F# is to get that goodness of ML programming and to make it fit in the context of .NET. So I've conveniently left a nice hole here for ML. Except I guess I've actually seen the approach used by the .NET team, which is by the C# design team, which is not just to take a language unchanged and put it into the context of .NET, but the sheer value that you get out of actually modifying a language if necessary, or sort of making a language fit in the context of a platform, dropping features that don't fit, adding features that do seem to fit well, keeping the core goodness of a language, but while making it sort of just feel right for working in the context of a platform. So I have changed, I've chosen a different name. I haven't called it ML.NET. It's not just a simple port of an existing language. There are potentially, I'm willing to sort of embrace the platform in whatever way is needed. But of course, trying not to lose that essence of core, of the goodness of core ML. So I want to compare it to the OCaml programming language. So I have taken roughly the same design as the core OCaml language, which of course was the same design as basically Edinburgh ML, which was done in the 70s and early 80s. It's slightly different design to what's called standard ML, which is it's a sort of a different issue, but the OCaml is by far and away the most popular version of ML that's being used today. So it makes a lot of sense to choose roughly the same core design. And I'm choosing it for roughly the same reasons as they chose it. The OCaml language has a number of extensions, such as modules as values, very large components which you can instantiate. You can have components parameterized by other components. And it's very nice from a theoretical point of view. It's actually not used that much by working programmers. So if you look in the SCV code base, it's only used in a couple of places in actually very simple ways where it's not strictly that necessary to use this feature. And actually people do make basic mistakes when using modules as values as well. There were some glaring mistakes in the SLAM code base where people just really didn't actually quite understand what was going on with modules. So I don't think in the context of this, getting a language to write components for symbolic processing, it just didn't feel right just to take exactly that mechanism and plonk it in to F#. OCaml has other extensions such as the O in OCaml, or the OCaml style objects, which are quite different to .NET style objects. They sort of have a structural subtyping. It's also sort of nice, but it's not actually used in practice by the ML programmers who are hacking up symbolic processing applications. It's quite interesting. It's more of a language design exercise in some ways, though people may argue about that. So of course both platforms have tools. So what do I add? Well, there are extensions, of course, to access the .NET APIs, and there are other extensions which I will talk about at some point. So there's a common language here. You can cross-compile OCaml, core OCaml code and core F# code. The F# compiler is done in that fashion. SLAM will be cross-compiled in that fashion. So it's quite a nice way to develop, especially if you've got an existing ML code base. Okay, so I just want to talk about sort of language design and orthogonality, and so the unification of concepts in an ML functional programming style of setting. So let's just take a pretty banal example, which is that, I mean, this occurs in Syme, occurs in loads of programming languages. In Lisp, tuples are multiple arguments, are multiple returns. So here we have a tuple, anonymous tuple here. We have the multiple arguments, function accepting multiple arguments, returning multiple values. And the concept of tuples just unifies the three sort of programming language features. And so you can apply F directly to args and get a result. So something that kind of still amazes me about programming languages is that, that this concept of having inner function definitions, such as G in this example, so we're using let to bind an inner function here, doesn't actually occur in our programming languages like C#. And this is actually an extremely powerful way to program. So first of all, there's a simplification in that whenever you introduce a binding, you just do it with the let construct, or perhaps with a let rect construct in the case of recursion. So no matter what you're doing, no matter what kind of value you're binding, it's just the same construct. And there's a certain simplicity to that for the programmer, that as they program, they want to bind something. They don't really have to think, will I make it a method? Do I need to pass it around as a first-class value and therefore make it a delegate value, or do I make it a static or whatever? You just sort of define it, and you define it either in its inner scope or you extrude it from its scope according to what's required. So I find that quite simplifying. And the ability to build up sophisticated operations in incrementally more sophisticated contexts is also, I personally find it quite compelling. I mean, I think I'm deliberately aiming F# at sort of medium advanced programmers, right? So people who can cope with this sort of thing. And there are also in some cases you need to be more explicit about your context in order to make the code easier to read. But here, this is fairly straightforward. We have an input stream. We build up an operation read based on that input stream. We build up some data based on the input stream. We build up a sophisticated operation out of those two operations. And then finally, at some point, we actually use these operations, or maybe it's a delayed reader, and we insert and we return lazy structures, which will use this sophisticated operation and compose it into the final result. So we have context, we have operations in context, we have operation in incrementally richer context, and then we use those operations. And just the combination of these two language features, let and capture, variable capture, just actually give a very powerful approach to standard programming tasks. So now perhaps talk about the most important difference between F# and other programming or other .NET programming languages, and that is immutability is totally the norm within F#. So you can't do this, right? When you go let something equal something else, the data is by default immutable. And so that applies to structured data as well. So if you have a record of data, as we have here, then these values, once you assign these into the object that you're allocating at this point, then the fields simply won't change. So it's hard. I can't quite get this, right? So immutability is such a powerful concept in programming. It just simplifies your whole, you just have fewer bugs when you have immutable data as a default, right? You can just rely that the object hasn't changed. That's the whole, I mean, it just sounds so banal, but when you're actually debugging sophisticated programs, this is so crucial. It's crucial in other ways, performance ways as well. So they can be aliased safely, you can transfer them between threads safely, and nothing goes wrong. You just have to, sometimes when I hear talks about the problems of aliasing, I actually have to really manually adjust my head. Oh yeah, of course, all the data is just mutable, isn't it? And so, of course, aliasing is a problem if you've got mutable data, but it's just not the norm, and it's, in fact, rare enough that you feel like, in most ML programs, you feel like the complexity is under control simply because you've had to be explicit about where you're using mutation. Now, that's not always true. You can, of course, build sophisticated data structures that use mutation everywhere. And have extremely complex invariants, but I mean, ML doesn't solve that kind of programming. It just makes you know when you're doing it. So mutability is available. So you simply put mutable on any particular fields of structured data that you want to be mutable, such as here. And you can assign an array. We can change what items is in this case and assign it a different array. Okay, so it's just this isolating and controlling complexity by choosing immutability as a default. That gets across that F# is absolutely a functional language. It's definitely an imperative language as well. It's quite close to C# in many ways from this point of view of analysis. It's a long way from Haskell in many ways, which is also in a sense of mixed in functional imperative language because I have these monads for controlling imperative effects. But you really can do side effecting stuff at any point in your code in F# if you want. You can print stuff out at any point in your code, for example. And if imperative programming is the right way to tackle a piece of complexity, then it's totally encouraged in the world of Camel and F# programming. You know, if you're building a graph as part of your symbolic processing, then you build it using mutation unless you have extremely good reasons to build it as an immutable data structure, as a list of vertices or something, a list of vertex pairs. So mutation in imperative programming is totally fine. Let's just talk about function values a little. So you know, of course, how function values simplify iteration constructs. So here's some examples of functions you can easily write. You see the polymorphism, of course, through the signatures. So that's no problem we all know those sort of things. And we know how a well-designed API that gives you a good set of these terms, gives you a good set of these operators, gives you incredible power when doing transformations over structured data. So I've already shown you also how function values simplify and unify the notion of extension. So you saw the example of evaluate, differentiate, and name. So they're just your virtual methods. And this is a subclass, right? You don't actually have to say subclass. You're actually just defining an instantiation of the extension point as a value. Okay, an operator is just a value that instantiates the record of functions. I mean,
but you can't. But you only have a subclass in depth 1 here, right?
what's that?
You don't.
Yes,
override.
yes, yes, yeah.
Right. So
yeah.
it's, I mean,
So I'm not saying this generalize the subclassing. What I'm saying is it gives you a mode of extension where you don't have to write the subclasses. Okay.
Right.
Yeah.
Right.
So.
But I can't. But I only create the inheritance hierarchy of depth 1. Just
Yes, yeah, that's right. So I mean, if you want to define, if you have types that add extra extension points, then of course you have to define new types for each extension point. But the instances of the extension point don't become new classes.
But you don't have subclassing, record subclassing.
No.
So then I have to write converters between these.
That's right.
I mean, which is part of the ML.
Yeah.
I mean, that's just part of the ML way.
That's right. Yes. But yeah, that's entirely right. Yes, I find this a clarifying way to think about extension, right? Because you're being quite explicit about what kinds of extension are possible, and you're not in the ML context. You're not tempted to use casting to the various subclasses in order to discover the new. You would adopt a different approach to service discovery, much more COM-like approach to service discovery if you wrote the APIs.
Going the other way around, is there an idea that you might, if you have a class hierarchy, be able to do ML-style pattern matching on it?
Yes, that's actually in the language. I haven't got a slide for that. So you can use in your pattern matching, there's an operator which you go : question mark, and then a .NET type. And that just does a simple type.
And you can
it's a type case operator. Yeah.
But you can go deep like an ML, a tree pattern? You can do a tree pattern?
That can be anywhere a nested pattern, but the only structured values you can pattern match are on F# values. So you can't, for instance, I'm not entirely sure what you do want to...
So for example, in ML, one of the nice things about pattern matching is you can say, I'm pattern matching on sum of product of sum. You actually can specify a tree pattern, right?
Yep.
Which actually sort of recurses down the heap for you.
So the corresponding thing from a .NET API point of view would be to first check that a value is, say, a particular subclass, then evaluate a property of that subclass, and check whether that property is of another type. Okay, you can't actually do the nesting by accessing the properties. Okay, you would have to expand that out into multiple pattern matches. Yeah.
Don, in this case here, do you actually implement this with classes, or do you implement it with delegates?
You implement it with however function types you implement.
Right.
Yeah, this is a value of. There's only one type class here, which is class unary operator. So functions are implemented as via virtual dispatch with some optimizations for certain calling conventions. So I will actually see that because I'll show the disassembly of. You'll at least see the type that corresponds to a function type. Okay. So I haven't talked about everything in the language. You've seen most of the other examples in the first demonstration: type parameters, discriminated unions, pattern matching, and recursion. And so that's the essence of the core language. Now I find when I'm writing sophisticated pieces of functionality that one of the most appealing things to me is I spend less time actually designing classes. So you can see, especially in the symbolic processing examples, that you don't have to design each subclass. You just give a value for the subclass. And I find class design quite a laborious process because you tend to feel that you should fill in the get hash code functionality, for example, even though it may not be strictly necessary for your application. And then you have to think about, well, how am I going to design the API to this class? I mean, it's important to do that at some point to do your API design. But I quite appreciate not having to write so many classes in this world. Okay, so no null pointers, I think, is a simplifying. Is often a simplification of the language. There are cases where nulls are important, especially during initialization, recursive initialization, and they do leak across from the .NET APIs potentially. So fewer classes and sort of some of the dangers of pitfalls of OO programming, such as this sort of thing, calling functionality before objects are fully created, tend to go away or tend to be less prevalent in the .NET, in the F# ML style approach to programming. So of course there's a lot of programming problems which aren't any easier in F#. I mean, you saw the iDisposable using pattern. I mean, so in these cases you just adopt the platform solution, and you get an awful lot of benefit in the context of F# by having it in the platform and being able to use all this stuff. You don't have to make design decisions in the language, and I don't have to do a library design, right? I don't have to do, or kind of control this sort of complexity, design how to control this sort of complexity. Okay, so my aim is that F# gives you the tools to concentrate on the complexities of symbolic processing. I think it's quite a good way to write client programs with .NET libraries. I think it's great for writing ML libraries. It's okay. It's not the view of the ML libraries from inside .NET is okay. You can access everything in an F# program. We'll see that in a bit. But I think it could be better at that point. And there's maybe language extensions to be added there. So I think there is a niche for writing these sort of sophisticated applications which have some symbolic processing components. Okay. So the F# challenge is, that's ML I've showed you so far, and some aspects of F# on .NET. Make it fit in .NET in a very practical way without losing the essential goodness of ML programming. So the first thing you need to do is cope with outward interop. How does F# actually access all the functionality in the world around it? So basically, it's quite similar. I learned a lot by actually having to modify the C# compiler and just how they implemented their dot notation and what the specification of it is. And so you just have a very nice dot notation in the language. So you can see lots of examples of it here. And you, for instance, when you create a new delegate value, you just give it a function value to go new delegate type and then give it the function to create the delegate value. So that works extremely well. So an interesting extension is object expressions. So these are just very much like inner classes, anonymous inner classes. So you create a new form. If you need to access it as at its base functionality type, you can give it a name here as base. And you can override methods here. You can only override methods in these object expressions. You can't add new methods, which is great because it gives you lovely type inference. And so we don't have to add any types on any typical overrides here. And it'll give you errors if you misspell on resize at this point. And this construct is orthogonal with the other features in the language, so with type inference. So capture, so you can nest these expressions inside each other. There's no this pointer in this. If there's a way of recursively accessing your objects, yourself if necessary. You can read about that on the F# website. That's got to do with this notion of recursive initialization. You can have mutually recursive objects if necessary, mutually referential objects, and yes, capture. So here we're capturing variables, title, and I don't think I use n. Actually, I don't even use title in this example. But let's assume that the variables, the arguments title and n were used as part of constructing the object.
What was this about not being at this pointer? Let me get that again.
So
like in this on paint, let's say you wanted to. Like,
yeah, you go as this.
Or size. Or
so
whatever.
the simple way to do that, I'll actually, I'll show you. Yes, it is an important point. So I'll just...
Man, you have a slide for every question known to mankind.
Except I've chosen the wrong one.
Meaning of life, you think?
Yes, I will actually. Since you raised the question, I will find this. Is that true? Extraordinary. So the style that you use is this sort of style. So if you have an object here, you're defining an object, and this is an object expression, and the object needs to refer to itself, you simply add a recursion at this point, because that's what recursion is about. You're just referring to yourself. Okay. So the question is whether so I mean, in my eyes, self is just kind of a half-baked. This is a half-baked version of recursion, because it's a single recursion to your immediately enclosing object scope. So the question, this sort of operator then extends to mutual recursion, where you have objects that mutually refer to each other as part of their behavior. The question then is whether this kind of recursion is actually sound or not. So when you're initializing this kind of object in C#, well, it's okay because it's sound because the behavior is a delayed behavior. Okay, so you're defining an object, but it doesn't, during initialization, it doesn't refer to itself, which gets across to this problem of calling virtual methods during initialization. Is it actually sound? So there's a feature in F#, which is what this paper is about. It's sort of I think it's quite a decent feature in the context of practical ML-style programming. You can potentially get failures during initialization if it turns out that you couldn't statically check that there was no recursive that it was a sound initialization, and that corresponds to a failure where you effectively call a virtual method during initialization. But you'll always get a warning if it can't statically check that this kind of recursive initialization is sound. So the short, the short answer to your question is you would actually go let rec obj equal the expression, then obj can be used anywhere inside the expression. You may get warnings that, in a sense, see, the soundness of that depends entirely on the fact that your initializer and all your setting up of properties or whatever you do during initialization doesn't actually cause the onPaint function to get executed. And it would help a lot, and it's quite interesting problem that if the .NET libraries came with annotations which actually sort of promised that sort of thing. You know, onPaint is delayed reactive behavior of a form. Okay, so the question is, I mean, there are people studying type systems for this kind of thing. I think it might be quite interesting to try and connect those two worlds. Okay. Okay, so that's very nice from a language point of view because it means you don't need this in a programming language, and you get nesting kind of drops out quite nicely. And you also get a lot less what I call explicit initialization holes. In ML, without that feature, you have to explicitly kind of create a null value in order to do your recursive wiring of your objects. And that is extremely hard to explain to programmers. Okay, so let's talk a little bit about inward interop. So how does F# code look to the rest of the world? So this is fslib, though. So unfortunately, F# does have a runtime component. It's not entirely... It'd be really nice if it didn't have any runtime components. It could just rely entirely on the platform. And I could, in theory, use system.converter as the implementation of function types, but it just doesn't... It's just not fast enough. So the type of functions compiles down to this type here, fastfunc, alpha, beta, and here are some other types you see as you're running regular F# code. So inward interop, as we all know on .NET, equals predictable, compiled, stable forms. You can look at the source code, F# source code. Part of the specification is F#. It will be compiled like this. You will see it from other languages like this if the stuff is publicly available. Okay.
Are you going to talk about what a fastfunc is?
Yes.
My delegates aren't good enough.
I'll finish up the slides and then talk about the implementation of closures. So here's what the differentiation example. F# values only compile to static members, static functions. So if you've got a true function in your F# code, such as these are all, such as the deriv, calculate the derivative, then you get a method, a static method in your underlying code. And of course, static methods alone don't make for a great API. And this is what I mean is you can access everything in the F# from C# and other languages, but it is all through static methods. So it's kind of, the big step is that we actually have fully functional inward interop. But you can't write what you think of as beautiful .NET APIs. You wouldn't actually author the .NET framework itself in ML. But that's why I say it's good, but it's not quite. I think there's more. Can be more work to be done there too. Okay, so inward interop is really essential for many purposes, and as far as I know, there's no. This has been, I think, the big killer for ML implementations. They've always concentrated on accessing external libraries, but very few people have concentrated on how can we make ML or Haskell or whatever else actually available to other programming languages, which is a real shame. But I think F# has tackled that problem in the context of .NET. Okay. So, of course, when I give slides outside the concept of Microsoft, this is the amazing part to everybody when it comes to, especially if they're a fan of functional programming, right? What's the win? And of course, the win is enormous gain of being on the platform. Libraries, tools, C# next door. So I think this is a really important point that F# gets enormous benefit from having C# just next door, right? If you want to access a C DLL, then you don't, or COM DLL, you don't write that code in F#. You write it in the unsafe subset of C#, which is perfect, a great language design, perfect for that task. So you get a component store. Everything that comes with the platform is just solves so many of the sort of side issues of which have inhibited the uptake of this kind of programming. So it's just amazing. Yeah.
Mix C# and F# in the same assembly?
In theory, yes. There's no net module. The C# compiler has an option to create a net module, and the F# compiler doesn't. But it's actually extremely easy to fix that if it was necessary. Visual Studio doesn't work like that, though. Visual Studio wants a single. Yeah, I guess you could probably get it to work to compile it up in the right way. There is an option on the F# compiler to statically link in everything that your exe depends on, up to and including the F# library. So you build a single standalone application that contains everything to do with F#, including any C# DLLs along the way. There's some limitations on that, but so in a way you can get that effect, yeah, but not exactly how you wish, perhaps. So what I mentioned to generics, as you know, we put generics in here into the IL and into C# and, well, now into the other languages. It's a very old slide from before. Yeah. But F# works with or without generics. So because F# doesn't depend, the semantics of F# doesn't depend on exact runtime types. You can use an erasure model for earlier versions of the runtime. And that's what happens if you're running on 1.1. If you put the right switch on the F# compiler or it detects it automatically. Okay, so it is available. So we're using it right just now for say the SDV project, trying to getting that to cross-compile. You've seen the Visual Studio integration and everything that comes with the download. Okay, so F# is a site for research. So it does raise interesting language design questions like the recursive initialization that I was telling you about. And I think this is a fantastic place to do research into safe mixed functional imperative languages, right? Because you've got online, on MSDN, you've got thousands of examples of real-world programming tasks which you can just translate across and investigate the problems that actually occur as you're trying to write those kind of applications in F#. For instance, or one of the F# samples is to do with concurrency and worker threads and automata. And you see lots of interesting stuff, again, actually to do with recursive initialization. Just dropping out of the fact that you can do such interesting kind of programs in the context of safe, statically typed programming, the traditional goals of ML. Okay, so I'll finish up there and then take questions on some general questions, then maybe go to Anders' questions on implementation of function types.
So how does it compare performance with OCaml?
Okay. You can usually get your F# code to. So say you put a day. You've got a 10,000 line F# application, and you put a day's worth of effort in with IceCap, the IceCap profiler. Then you can get your code to run within, say, a factor of 2 of optimized OCaml code. It's nearly always faster than OCaml bytecode. There's a couple of constructs that the CLR implements extremely badly, such as exception throwing. So the first thing you have to do is eliminate all use of exceptions for control. Okay, and that's very helpful in Visual Studio because it just says print exception, raise, and you just go through them until they all disappear. Right, and they're nearly always you look up a map and catch the not found exception. Beyond that. So, I mean, performance goes beyond just how fast the 2 programs run. It's also whether you can find the performance if you've got a good profiling tools available. So, often you'll quickly spot your performance, the places in your ML code that are causing performance problems much faster than you would in the context of OCaml. And it's the same argument with C# and C++, for example. It depends on. Sorry, I guess C++ you always have IceCap available as well, but OCaml doesn't have great profiling tools. Yeah.
It's been a lot of years since I looked at ML, but one of the beautiful things about it was always its beautiful type system and the type inference. And my memory from the mid-'80s or whenever was that as soon as imperative constructs were added, the whole type system just fell on the ground. Everything came down to ground types. The polymorphism went to heck. Is that still the state of the world?
No, not at all. So they in the early days of this kind of work, they got themselves into awful problems because ML doesn't have an explicit binding syntax for type variables. You're not being explicit about when something is polymorphic. And they made some mistakes about inferring things to be polymorphic when in fact they couldn't be polymorphic because in particular because you could mutate them, and if it was polymorphic you could put an integer in and then you could put a string in or something like that. But that problem doesn't occur anymore in these language designs because of a very small restriction, which is things that are polymorphic must actually be simple values. Okay, they have to actually be functions or they have to be constructed data. Okay, so you will occasionally, as you're writing ML code, hit this restriction, but it corresponds exactly to restrictions in the .NET world anyway, that you can't have an object that is actually polymorphic unless it's got a generic method. But the object itself has a known type. It can't actually be a variety of types, except for the null value, which is sort of a variety of types. Yeah.
Shall we see stuff like Isabelle then in .NET soon?
You can definitely do theorem proving. Yeah, sure. Yeah. So the set of samples, which I think there's John Harrison has an extremely good set of all the basics of symbolic theorem proving through propositional logic, first order logic, decision procedures, all written in OCaml, and in basically the subset of OCaml I'm talking about here. And one of the things we'll do in the next 6 months will be to get all of those as a sample in the context of F#, and maybe some visualization added to it. So that's what you can add as well to the sort of basics. Yeah.
Continuation passing style, and do you use that in F#?
No. Okay. So that sort of compilation approach sends your interoperability to the dogs. Right? So you really want a close correspondence between your source code and your IL. And F# has to do enough work to insert closure classes. And I mean, it's not too dissimilar to what the C# compiler is doing with anonymous delegates. And yeah. So.
The XIL has a kill call instruction.
Yep.
That would be useful in making continuation passing style.
To be honest, not by itself. You need other. I mean, it can be used as a compilation technique. I mean, there's SML.NET compiler does a CPS transform. So tail calls are the other thing that aren't implemented very well on the .NET platform. So they're used by default, but there is a no tail call switch to get rid of them all. Of course, your programs may run faster as a result, which is a bit, yeah. So, yeah. So you just have to make sure you don't use an infinite amount of stack in your program, and you can turn the switch on. Yeah.
But F# doesn't have first-class continuations to kind of tie into that.
That's right. It doesn't. Yeah. No, of course not. You couldn't. Yeah. Very few ML implementations ever have. Yeah. A few have. Yeah.
So you're talking about you don't have the null reference problem, but with the refs, with the mutable pointers, basically, you can have that. You can accidentally.
Of course.
Set it to null. So really, it's just the fact that you're immutable that sort of wins in terms of null references, right?
Yes, but the problem is if you don't have these recursive initialization constructs, then you end up having a lot of nulls or some sort of an initialization hold in order to be able to just get your data structures wired up together. And you see that in graph programming, and you still see it in F# when you have graph programming. So nulls sort of stem out of other language design decisions in many ways.
But I'm curious about that, because in ML, core ML, you don't have null references. Every reference points to something.
That's right.
So is the notion of references in your core ML different?
No, it's different during these recursive initialization blocks. Right. Then you have these delayed evaluations which hide the null, the initialization hole. There you can have nulls. Yes, they're just lazy.
But if I'm not doing that, if I'm just in the pure ML, and I don't have null.
That's right. It's in normal old ML, you're not getting any warnings about using this fancy recursive initialization feature, then there's no chance of getting null exceptions, except when doing .NET interop. Yes. Yep.
I'm looking at the website at the moment. Is there any plans to support functors and higher level module type stuff as template type classes, or?
Various thoughts ticking around in my head. Yeah. So I mean, functors have, in terms of ML style ML, functors have their uses, certainly with say set and map and basic data structures. I think you're talking about sort of more generative programming or sort of a higher notion of generic programming. Yeah, I'm not sure. I mean, there are also platform approaches to that problem arising through Anders' work. So I'm not sure where it will go. I mean, yeah. But certainly, I mean, being able to extend your compiler to do sort of complex code generation at compile time gives you a lot of power. Or, I mean, in recent C# design discussions, be able to extend it to do the code generation or to manipulation of programs at runtime through sequence operators and the like is also very powerful technique. And it would be quite interesting to extend a language like that like F# with exactly that approach. Yeah, so. We'll go to just gone five minutes over. Do you want to see the implementation of closures?
Yeah, and one thing actually that might be interesting too is just from a more commercial perspective, how large is the ML community? And what are the market opportunities? And I mean, we're obviously doing zero from a commercial perspective these days, and so.
Yeah. So I think there's an unmet need in the market, right? I mean, there's an unmet need, I think, in Microsoft, and to me that means there's an unmet need in the wider market, and I get plenty of people interested. So OCaml, I kind of asked them about number of downloads. OCaml comes out of the box on most Linux distributions now, so it's hard to tell just from download statistics, but they talk, I think, like 10,000 downloads a year or something was last time I asked 2 years ago. So it's a little bit hard to tell, but what you really got to try and assess is the entire market for symbolic programming and how sort of how high value are those customers as well. Right? And they do it feels quite high value. I mean, many of these people are using Unix systems, for example, because they feel that whole world supports scientific computation or symbolic processing somehow better. Yeah.
But I heard from the OCaml guys that they have trouble with the OCaml consortium for people actually paying for kind of support.
Oh yeah, yeah.
So,
Oh yeah, I know. I don't know if there's. I'm not saying there's money to be made. Yeah. I'm saying I think there's platform adoption to be.
I think I would say it another way that there's huge use of it. I think in academia, and this could just generate incredibly goodwill just as PR. Just to have this. I mean, there will be some friction as well. We just talked about that, but I think just when people see this interop, I mean, it's really compelling, and it goes beyond just what you see in the OCaml environments and the other environments. You would just be crazy not to sort of pick it up. So I think there could be just a tremendous benefit that way, as well as getting more interaction, substantial interaction with the researchers.
Yeah. So my approach has always been to make sure everybody just thinks of it in sort of understands that, first of all, that it's a demonstration of how functional programming can be made to fit and how programming can look quite different in the context of .NET. And make it available as a viable alternative. But the main thing is, there's lots of different goals, but sort of conquering the world with functional programming isn't necessarily one of the necessary.
No, I totally understand that. I'm just wondering what would be, what is the correct approach here in terms of building a community? And I mean, I can see how this has tremendous value in terms of lifting VS into sort of the higher echelons of academia and whatever, where traditionally we haven't had them in, so I think it's could be extremely valuable for that. I'm just wondering, what is the approach?
Yeah, I'm not certain of the answer to that. I think it needs all the right people to sit down and really agree that we actually need to tackle that, to fill that niche. And it may or may not be with F#. You may actually choose to do it with something else, or you may choose to adopt the approach. You may put out Microsoft FP, functional programming, or whatever. It could be Haskell, if necessary. I mean, F# is nice, but then if you're only going for the academic market, then maybe an implementation of Haskell or strict Haskell or something would also be appropriate. But above all, you have to get the other people, the academic world, involved in that process. But that's a very thorny process, because working with the academic world and the fragmentation of this kind of programming in that academic world is very high, and it's quite hard to get for Microsoft to unify that in some way.
Are you, just out of curiosity, are you aiming to make it a deliverable, like with tutorial documentation?
Yeah, that's on the web. Yeah, I've done all that kind of thing. So, but I'm trying to keep it small as well. And I think that what you've seen is the extent of the tools that I'm interested in. Maybe we do IntelliSense, maybe whatever in Visual Studio, etc. That's the sort of fun side of things. But it's great. It's just so fantastic that in the .NET world you don't have to think about adding more and more tools in order to satisfy that niche. Yeah.
Along those lines, you contrast for me the pragmatics of experimenting with F# versus SML.NET.
I think, I mean, neither system has had other people experiment with language additions, right, into the language. Do you mean experimenting as a programmer, or actually adding?
From the programmer point of view.
Not adding the language. You just mean the
implementations themselves. I mean, what is different in F# versus SML.NET?
SML.NET, right. So ignoring the language side of things. So I'll address both. So on the language side of things, my big focus has been on the story I've told today, interoperability, and getting it to fit. They also have concentrated on that, with the exception of inward interoperability isn't a big focus for them. On the implementation side of things, they're also very interested in advanced compilation techniques. So they do a whole program optimizing compiler for the ML. So you give all your code to the SML.NET compiler, and it does very advanced optimizations, which is one reason why inward interoperability is hard, because all the representations sort of get munged a bit by the compiler. So what should be publicly stable interfaces don't get compiled. Things like functions get compiled in very wild ways. And they get very good performance out of the SML.NET compiler because whole program compilation can get you huge benefits. Whereas my approach is much more like the OCaml approach to optimization, which is just straight from the source code, parse it, type check it, run a pretty decent but fairly straightforward optimizer over it, and generate the IL code at the end. It's very, very straightforward, just separate compilation of assemblies. Yep. So of course there's plenty, both those implementation techniques can be applied into both languages. There's a separate issue about the languages, a separate issue about the implementation techniques. Yeah.
So when you talk about, I think you call it outward interrupts, how do you deal with overloaded methods? How do you kind of expose them in F#?
Yeah, so I mean, it's well known that you run into problems with subtyping when you have to constrain satisfaction problem when you have these overloaded methods. So F# hits that as well. If you have complex overloading, you might have to insert, as you saw, I had to insert a box there, which of course cast it to the right type. But you may have to insert type information hints to indicate which overload you're using. But it drops out very nicely. I mean, it's very obvious where to add an extra type constraint in order to select the right overload. I mean, you just constrain your types enough with extra type annotations until you get the right overload. Of course, the .NET libraries they use overloading, but actually in quite a nice kind of way. So it depends a lot on the use of the overloading in the target libraries as well. Yeah? Yeah.
So Eric was mentioning that you don't have full continuation into the F#. I'm wondering, is your continuation support mostly to allow full closure to work correctly? There is no relationship, or
continue. I mean, there's no. I mean, if you're talking like scheme-style continuations, there's nothing like it in F# at all. I mean, you just have function types and function values, which is not the same thing at all as capturing the execution context, which you're doing in a continuation.
So the question is, how much do you think is language suffering, or how much you cannot do in language because of?
I mean, ML implementations are very, very rarely supported continuations. It's not.
So you really don't think it's a big deal?
Not for what I've talked about today. Not at all. I mean, the continuations are extremely powerful sort of underlying device, but if they just have such effects throughout your virtual execution environment they're extremely unlikely that languages that support continuations will be viable in a platform setting for 20 years, right? 10 years or 20 years. Yeah.
So I think it's a quarter up for those who want to stay on and get into maybe some more technical discussion. We have another 15 minutes, but I'd like at this point to wrap things up. I want to thank you for giving this presentation. For me, this is one of the best Christmas presents I've ever gotten. It's very, very cool stuff. Thank you very much. Thank you all for coming.
Hey, how are you, Brian?
Yeah,
nice to see you.
Yeah. What do you need from us?
From you guys.